Hello, everyone. Today, we want to talk about what happens and when countries actually decide to shut down the internet. I think this is not imaginable for most of us that one day we do not have internet. But yes, this happens. But before this, today, I'm an executive consultant with CGI, but before this, I was a network security network guy, let's say. And I have done lots of projects in this area. But when it comes to my favorites, packets is my first one. Protocols, logics, these are things that I really like to work with. So if you wanted to keep in touch with me, I'm too old for Instagram and too soft for Twitter. So please use LinkedIn, and it would be my pleasure. Before starting, I just want to remind that this talk is solely a independent technical research. It's by no means it's a political messaging, and all the opinions are mine. It was June 13 at 6 a.m. and I'm waking up to these messages. These are in Persian, my language. But if you're curious what it says, "Hi, are you awake?" I wasn't. "Have you heard from your family? Are they okay?" And who is my family? He's talking about my wife and my son that happened to be in Iran back then. I jumped out of the bed, opened all the news channels, and I realized that, okay, there's a big war happening between two countries, Iran and Israel. And it's getting worse. Mr. President, after 4 days, messaged everyone should immediately evacuate Tehran. And before this, I have started planning it, but it was really difficult because it was complete chaos. A closed sky, no fuel, you could name it. Everything went wrong. But still, I tried to plan the evacuation of my family from Tehran to another city, and from that city to outside the country. And this is my real notes back then. But my plan needed communication with them. And I was in Munich, in Germany. So the only way that I could really contact them was through internet. But on June 18th, the internet went down completely. They call it a stealth shutdown because there was no internet. No one could communicate from inside outside, from outside to inside. And before this, it was getting, the symptoms were, okay, this is going somewhere, bad. So before and after, it took, really days before it can be recovered. But the question is, this was my story, but does it happen in other countries? The answer is yes. Based on a study done by Freedom of the Net 2024, basically 30 countries, almost 30 countries, are doing this from time to time at different scales. So it's not only the country in the Middle East. We have lots of big names like China, for sure, Saudi Arabia, India, Pakistan, Turkey. These are all the countries that they are doing, internet censorship actively. But how actually this happens? This is where it gets technical. But before going into the tactics and the techniques, we have to recall that there are 4 major technologies that are shaping the modern internet. Encryption, DNS, BGP, and fiber optics. The last one provides the connectivity. BGP ensures the network layer reachability. DNS translates domain to IP, and encryption provides confidentiality, protects our privacy, and integrity if authenticated. But for this to work, the censorship, they need central points. With central points, you can create control points. How? This is you, this is me, internet user. We usually connect to a mobile network operator or a fixed internet service provider or a satellite provider. Each and every of these providers, they have their own gateways. These gateways are connected to domestic online services, providers, content providers, government online services, and these are in turn connected to the national gateways. This is the central infrastructure or the architecture of internet in many of the countries in the world. But it's not the case with Germany, to the best of my knowledge, for example, and I will tell you later. But these gateways internally are interconnected. How? They are getting connected through IXP or Internet Exchange Points. These are basically, high-capacity switches that, big internet providers are connecting directly and, peering on top of this physical connectivity. But this is going to become the border between the user and the free world. But still, these countries need to be connected to the internet, right? Here is the internet. And internet is being provided by different tiers of service providers. Tier 1, Tier 2, Tier 3. Local, regional, and global. So these tiers are shaping the big internet. And this is the structure that the national gateways are getting connected to these tier 1 or 2 service providers, again through BGP. So this is the central infrastructure. But when it comes to tactics and techniques, it depends what layer we are talking about. If it is application layer, it is usually about DNS poisoning, SNI filtering. When it comes to transport layer, it is usually done by TCP reset injection, by packet dropping, tampering, and traffic throttling. In the IP network, or in the network layer, IP blacklisting was the old one. BGP manipulation is very common. APN filtering is another one. When it comes to physical layer, you just unplug it. Okay, so let's start with DNS. What is DNS? Machines use numbers. We are good with names. DNS translates it, right? Okay. But it's not that simple. This is the DNS based on the standard. RFC 1034, 1035 has basically defined this protocol. And this is the header of the DNS protocol or DNS message. But one thing, and this here down, presenting a standard healthy query response discussion between the client and the server, right? But here we have an ID. This is here. The ID. The ID basically is identical between a pair of query and response. You're going to need it. But when it comes to sending query, this DNS message has to be transported over something. The very common one is UDP, and it uses 53 as a port number. The next one is TCP, again, 53. TLS, 853. DNS over HTTPS, 443. These are the common transportation for DNS queries. But now, let's talk about DNS poisoning. What is DNS poisoning? Simply, you ask, what is the IP address for Google? And somebody tells you this IP. And you trust them. But that guy is a fake one. But still you trust it. This is DNS poisoning. Let's take this real packet. This IP address, 100, 400, this is just anonymized a version of it, but it's real traffic. Somebody can somebody please tell me what is strange in this picture? Anyone? Come on. What? The third? What is it? Yeah, but there is something very strange here. Imagine. Thank you. 888, Google. 999, it's quad 9, I think. These are all public DNS resolvers and very trusted. But look at the response. For YouTube, it starts with what? 10. 10 is a private address. How come? How come 888 responds to my query for YouTube with a private address? Something's off. Agree? So, now let's zoom in. This is my original query. And these are the two responses. One is red, one is green. But let's talk about first the transaction ID. You remember? It has to be identical between all the query and all the responses. It is already identical. But one tells an IP address from a private range, but the other one, it looks legitimate IP, right? But we have to dig in more. The first DNS dissection belongs to the query. The second belongs to the first response, and the last one belongs to the last response. Something is strange here, but it doesn't lie in the DNS protocol. Look at here. We have an internet protocol header here, correct? This comes with an identification ID. This belongs to IP header. And it has a time to leave. What is it? 1728. If you check the RFC 791, identification ID is being assigned by the sender. So, if I have sent a query with an identification, the response should have its own identification. But look at this green, the red picture. What is it? 1728, 1728. But the green, 47EA. What does it tell you? This red packet is just a copy of my own query. So something happened in the middle of the way. I have sent a query. A middle box just received that query copied the packet and resend it to me. The only difference between the query and the response from the middle box is this IP, 10.10.10. But it tells me something else as well, that this middle box, whatever it is, it has not dropped my original query, and my query has already reached to the final destination, which is, in this case, 888, right? This tells me, because I'm receiving a response, and this response is a legitimate one, and I can tell from first the transaction ID, because it tells me it belongs to my query, and second, it has a genuine IP header. But if I check the DNS cache on my machine, after this query and response discussion, I will see in the cache 10 as the IP address for YouTube. How come? Good question. It is because our resolver, the operating system, takes the first response as the main one, and it discards, ignores the other packets. As simple as that. You see? Logics, protocols, packets, they do not lie. They just, they are beautiful. Seriously, I mean, you can make sense out of it. And this is how it works. But this was a DNS over UDP. DNS over TCP. What is strange here? TCP has a handshake, right? I send the first packet as a scene. Then I receive another packet in response with a scene and ACK flags, right? Set. And then I send an ACK. So I see these three packets. So the handshake went well, right? Then the client sends the original query, right? This one, in green. Standard query with this transaction ID. But what happens after that? This is TCP, right? I'm getting TCP retransmission. Is there anyone that can tell me when you will get TCP retransmission in network? Absolutely. When the packet is lost, or for any reason, the timeout, the timer that the application is using for that specific packet has already expired. So when it gets timed out, then TCP, the client, tries again and again and again and again. Hence, you're seeing different retransmission packets here. But it shows that that middle box drops this DNS over TCP straight. How about TLS? What is TLS? So it's an encryption transport protocol, right? It encrypts everything. So what does encryption mean? It should be only between me and the ultimate destination, correct? And no one else should be able to make sense out of this conversation in the middle of the way, right? But it's not the case. How? Again, if you look at the TLS protocol and you read the RFC, the standard, you will see the TLS has its own handshake mechanism. And this handshake starts with sending client hello. But before this, again, we have this three-way handshaking. But what happens after client hello? Sending client hello from the source to the DNS resolver. Again, TCP retransmission. So it means that middle box, whatever it is sensitive to DNS traffic that goes over TLS. It drops it. How about DNS over HTTPS? At least we do not see any red thing here, right? And it's true. It works. We have the TCP handshake. We have the client hello. Then the server hello. Application data. This is a genuine, healthy TLS communication between source and the destination. So it works, right? That's a good news. So if next time I set as the client my DNS to use HTTPS as the transport protocol for sending and receiving the queries, then the mailbox cannot do or mess with it, right? No. It doesn't work. The previous one was between Cloudflare. This one is with Google DNS, right? What is the difference between these two? Again, the story is the same. Client hello, we send it, no response, we cannot hear about it again, so it drops it. But what was the difference here? Absolutely. Here, we are using TLS version 1.3, but here we are using 1.2. And you will understand why it is so that TLS 1.3 is somehow, it looks, resilient, but 1.2 is not. Any questions so far? How what? Okay, that's a very good question. Here is the answer. There's a big irony with encryption. And that irony is every encrypted session begins in plain text. That's how. Why? What does it mean? So I just asked GPT, what portion of the web traffics or responses or queries are encrypted? This is his response. Not my problem. Seriously. But we can, relate to it. It's more than 90%, right? So this protocol, TLS, accounts for more than 90% of the traffics, plus another protocol, it is called QUIC, developed by Google, and later were standardized. But we have TLS version 1.2, and we have 1.3. It is a standard number is 5246, and this one is 8446. And there is a 10-year gap between 1.2 and 1.3. The big difference, am I at 5 already? Okay. So, the big difference is between the negotiation, the handshake. But if you want to know, in the TLS version, there is a field in the client hello, which is being sent in plain text. And this SNI shows the actual target server. And again, this is plain text. That's how the mailbox can understand and provides enough information for the mailbox as to what is the intention of this traffic. If it is not something that I do not like, then I drop it. This is how, right? And there are some other ways of doing, messing with encryption. One is protocol fingerprinting. This is done again by the mailbox. You can later check JA3 and protocol degrading. For example, QUIC as a very nice encrypted protocol has nothing, it doesn't work in many other countries. Why? Because it's very secure. And they do not like it and they drop it. That's simple. Finally, the BGP. BGP is the routing protocol that shapes the internet, right? This is the standard for BGP, but I want to show you here. There is a peering relationship between routers on internet when it speaks, BGP. And this peering is between one AS and another AS. This is a logical, boundary for any network inside the internet. In the free world, if it is physically or, feasible, every AS can, create a peering relation between one another. But it's not the case, again, in many censored areas or countries. So they drop it. They do not allow it. Because if you can do this, then you can circumvent all these middle boxes, right? A healthy BGP relation starts with one AS, the legitimate one, sending and advertising the IP address with showing the AS number of himself as the origin. And this propagates all the way across all these ASs that have peering with one another until the AS that I as the user is connected to, right? And this is how, when I want to get to 1.1, and if I trace route it, I will send my packet to the gateway of this AS, this AS, this AS, and then it gets to this AS, and I will receive the reply message. But when it comes to BGP, hijacking, something strange happens. That AS that wants to hijack the BGP create a fake advertisement of the same IP address and propagates this route down to the local ASs. And in the result, what happens here is that when I want to access the legitimate one, basically I'm being rerouted to the fake DNS. This is how it works. But sometimes it gets really messy when the AS, or either intentionally or by accident, leaks this fake route into the upstream peers. When this happens, you will see this news headline here. Telegram is being hijacked, and all the traffic globally or part of the, in the world were being redirected into a route that was not safe. This is BGP hijacking. And finally, in the layer, if nothing works, they just unplug it. And this is how we finish. Thank you. Thank you.